Hello and welcome to today's video. In this video, we're going to talk about the first application of derivatives, and that is monotonicity of functions. The idea here is if the derivative gives us information about the slope of a function, then that means we should also be able to infer whether a function is currently increasing or decreasing. So we would get information on the monotonicity. And to make this more precise, we'll introduce the necessary notions first, and then we'll talk about inferring monotonicity from the derivative of a function. So this section is called monotonicity. And as usual, we'll start with a definition. So we'll first define precisely what we mean for a function to be increasing or decreasing or monotonous. So as usual, we'll just define this on an open interval, but of course you can usually do this in a more general way. But as we're interested in the connection between differentiation and monotonicity, we'll just apply this to functions that are differentiable, and we define that for open intervals. So let I subset of R be an interval, and for monotonicity we can include the boundary points, and we just assume we have an interval, open or closed. And let F be a real valued function defined on that interval. Then, first part of the definition, the function f is called, we'll start with increasing, and we'll also define what strictly increasing means. On this interval I, if the following holds, well, if f of x is less or equal to f of y for all xy in I with x strictly less than y. So if we select the point x and another point y that is to the right of that, so higher on the real line than x, then the function value behaves in the same way. F of x is less or equal to f of y, so the function increases along the way. So that is increasing. And of course, strictly increasing, the difference is simply that we require f of x to be strictly less than f of y. And again, we want that for all xy in I with x strictly less than y. So this is the strict version. And of course, if we can find a function that is strictly increasing, we can also define a function that is strictly decreasing in a very similar way. So that is part 2 of this definition. That says the function f is called decreasing or strictly decreasing on I if, and once again, now we want f of x to be greater or equal to f of y, with the rest of the setting being the same. So for all x, y in I with x less than y. So again, we take 2 points, x, y being to the right of x, and then we want the function to be decreasing. That means the function value at x is higher, and then the function decreases towards y. So that's decreasing, and of course, strictly decreasing is almost the same. We just replace the greater or equal to sign here by a strictly greater than. So again, that is the strict version here. And finally, part 3 of this definition, a function is called monotone or strictly monotone if it is either decreasing or increasing. And for strictly monotone, of course, we require strictly increasing or strictly decreasing. So the function f is called monotone or strictly monotone if f is either increasing or strictly increasing or decreasing or strictly decreasing. Another question is, of course, how can we derive monotonicity properties of a function from its derivative if the function is differentiable? And as I said, the idea is that the derivative of f yields information on the slope of the function. And of course, that means if we have a function that is positively sloped, then that function will increase. And if that holds for an interval over a whole interval, then a function will increase for every point on that interval. And the same is true for a function that is negatively sloped. That means the function is locally decreasing. And if that holds on an interval, then the function is decreasing on that interval. So obviously that is true. Of course, the derivative may also have a value of 0. What that means is locally, the function is not changing a lot. It might still be decreasing or increasing, but we would not be able to infer that from the derivative. So basically, we can only infer this information if a function has a strictly positive or strictly negative derivative. On the other hand, if a function is increasing, then of course the derivative has to be positive or at least non-negative. It may be 0. But the other implication is not necessarily true. So let's write down that as a theorem. So that's the monotonicity criterion for differentiable functions. So of course we now need that I is an open interval, so that I subset of R be an open interval. And of course that may not be the case in practice. So if you have a function that is defined on a bounded interval, for example, you can take the open interval by just excluding the boundary points, apply that theorem there because that's the interval where you might be able to differentiate that function. And once you have that result, you'll also have to have a look at the boundary points separately and see how those compare to the results that you get for the open interval. And that's always the case if you want to know about the behavior of a function on a closed or partially closed interval. You'll just have to look at the boundary points separately if you're able to infer the behavior of the function within the open interval through differentiation. This just does not extend to the boundary points, so you'll have to treat those differently. But we'll come back to that point in a later video. So again, we'll have an open interval. And as usual, let f be a function defined on that open interval. And we want that function to be differentiable. Then the following hold. For 1, If f is increasing on I, then the derivative needs to be non-negative. F is increasing on I, and of course the reverse in this case is also true. If the derivative is non-negative, the function is increasing. It doesn't have to be strictly increasing, but it still will be increasing, and that of course includes the possibility of the function just being constant. So f is increasing on I if and only if f prime of x is greater or equal to 0 for all x in I. Now the reverse, or the version for strictly increasing, is not reversible. So here we have the implication if f prime of x is greater than 0 for all x in I, then f is strictly increasing. However, as I said, the reverse may not be true, and we'll see an example of that in just a second. Part 3 and 4 will be about decreasing functions. So similar to part 1, f is decreasing on I if and only if f prime of x is less or equal to 0 for all x in I. And part 4, again a strict version, if f prime of x is negative, strictly negative for all x in I, then f is decreasing on I. Strictly decreasing on I. Again, as a quick remark, as I said, strictly increasing or strictly decreasing does not necessarily imply strict inequality for the derivatives. So in general, strict monotonicity does not imply f prime of x is positive or negative. For example, consider, for example, the function f of x given as x to the power of 3. You should know how that looks, but basically that function is shaped like this. So this is x to the power of 3, roughly. And as you can see, that function is obviously increasing, and it even is strictly increasing. So that is strictly increasing on R. But if we consider the derivative f prime of x, that is 3x squared, so f prime of 0 is 0, and that is not strictly positive. So this implication is just not true. What we can infer here is that the derivative is non-negative, so the function will be increasing, but we don't get the strictly increasing from the derivative. Okay, so the function is strictly increasing, but still the derivative might be 0 at certain points. So this is how we can infer monotonicity of a function that is differentiable. And in the upcoming videos, we make use of that fact to see if we can find out anything about local optima, local minima or local maxima, and of course in turn also global minima and maxima of a function. And as usual, I'll see you then.